All right, guys. Good morning, everyone. Any questions about the homework? Going well or not? This is your time to ask me some questions if you can solve it, because due tomorrow. Remember? So anything I can help clarify. It wasn't clear from the lectures. No? I have some good news for you. If you didn't check the emails, you can go here to YouTube, and they are already uploaded. All the classes, I'm going to continue uploading all of them. I have some bad news, though. First one, I was looking at the videos. They're quite boring. Okay, so I'm going to try to be a little bit more cheerful to make these videos a little bit better. And second, you guys can see it over there as long as you don't touch the cable, okay? Or you can plug it and unplug it very quickly if you want to. And second, I need to fix some the audio issues. There is one lecture in which the audio is not great, and there is another lecture in which there is no audio at all. So I'll try to see if I add subtitles or if I can add audio on top of that. But I'll try to fix that. If you have any questions, just let me know. So I'm going to continue uploading all the videos. And I have figured this YouTube thing now, how to upload videos quickly. So it wasn't as bad as I thought. And actually, you can do some editing there too, which is very, very convenient. So I have to do a little bit of editing to some of them, but the videos are going to be there. Okay? And one more thing is that Jeffrey has been working very hard in order to upload the homework solution. So, okay, let me come back here. If you go here to more resources, this goes into a folder where I'm putting some of the files that you were using already and some of the widgets that I was showing you just to show stresses or anything, varying some parameters to understand what is the influence of those parameters. And you can download those and upload them, make them run with Python to see how they work. But also here, if you go to this undergrad homework folder, you will see that Jeffrey already added here homework number 1. And in homework number 1 solution, if you open this file, you will see all the solution with this Jupyter notebook. And actually here, you see you have all the data already compiled. Jeffrey is very good. He's very neat in writing everything. And I think he borrowed, you see here's the solution. And here you have all the code, right? All the code that you need, you can get it from here too. The most important to me for the homework is not that you learn to code, but is that you learn the concepts. Coding is also very useful, and it may be a very good resource for you in the future. So you may take the code from here and try to run your homework later to see if it works with that or not. But the most important thing are the concepts for now. Here you have problem number 4, and I think he borrowed this from some of you. I don't know if he added the credit here or not. Yeah, here's the credit. So thank you very much, Nathan, for that. And that's working very well. So check the homework solution there. And he's going to work on homework solution number 2 to have it by Monday. Yes?
Question 4 in the homework, do you care what minutes we put the answer in?
In this one?
The homework that we have to submit tomorrow?
Tomorrow? If it doesn't say, no, I don't care. But sometimes I really want you to change units to be comfortable with both SI and field units. So in that case, yes. If it says, answer in MPA, you should give the answer in MPA. Okay? I don't care which way you go. If you go first through PSI and then you get to MPA, or if you go through MPA and you get to PSI. I recommend, though, that you go through everything calculation all on SI, and then you come back to field units. Because otherwise you have to use some factors there to correct your formulas. But as soon as you get the right solution, I don't care. Okay? All right, so you're now working on homework number 2, and this one will be uploaded soon. Also for next week, remember that we have an exam on October the 5th, right? So let me pull out the calendar here. We're at 1 week from the exam. And I'm going to try to cover up to homework number 3, but I'm not sure when I get there, okay? I have already assigned the homework to be due on Wednesday for the new one. But I don't know when I get there. I'll try, okay? It's not too much. It's not too complicated. But we need to get through the concepts for that, and that might take a little bit. If we don't get there, don't worry. We'll change the objectives, but we'll try to get there, okay? So finish the homework. I'll upload the solution as soon as you make the submission, so you can check on that. And it's very important to me, as I told you in the email, that you train with problems before you go to the midterm. If you train a little bit in this, all these problems I gave you, you will see that the midterm will be very easy. But if you don't train, then it's gonna take a lot of time. You may get confused. You may see numbers that you never saw before, and you don't know if they're gonna make sense or not. When you solve the problems, the most important thing is you check the numbers and you make sure that they make sense. Okay, so let's continue with the lectures. I don't know if you have realized, but with these equations that we saw last time, we now are able to calculate horizontal stresses. Usually in these kind of calculations, instead of using L08-1, L08-2, which are like mathematically correct but don't tell us anything meaningful, instead of that we use sigma h mean, which is the minimum tectonic horizontal stress, epsilon h max, which will be the maximum horizontal tectonic strain. From here, instead of calculating sigma 1 and sigma 2, we calculate sigma h mean and sigma h max. It's exactly the same equations. I'm just changing the meaning of those, okay? And if, for example, we want to calculate sigma h max, and let's say sigma 2, epsilon h max is going to be here. It's going to be in the same orientation of the stress. And once you calculate those effective stresses, you just have to add pore pressure, and you can calculate SH mean and SH max, which are going to be equal simply to sigma h mean plus the pore pressure and sigma h max plus the pore pressure. And this is a very, very important finding, because now we're able to calculate horizontal stress. If you remember back in the first lecture or second lecture, we said we can calculate vertical stress, but we cannot calculate horizontal stress because we don't have enough information. Now we do have that information, and that information comes from the properties of the rock, its Young modulus and its Poisson ratio. With those two, now we can calculate effective stresses. And let's see why it is important to calculate horizontal stresses. So now we know this value, SH mean and SH max. So let's say that you go to the Permian Basin, and after drilling, you want to do hydraulic fracturing. and you're interested in doing hydraulic fracturing on a given formation at a given depth. Actually, this weekend I did go to the Permian Basin. I went to visit a friend there in Midland. It's amazing the amount of wellheads, jack pumps, and drilling rigs around there. So, from some time ago, we already knew how to calculate pore pressure. We already knew how to calculate vertical stress. If you remember that was an easy one. And now, with the new tools that we have, which is elasticity, we can calculate what is SH mean, let's say somewhere over here, and we can also calculate SH max. I'm not going to make a lot of emphasis now on SH max, but you will see that this one is important too. Now that we have those values, why is SH mean important? What is SH mean going to give us? What kind of information? Any guess? The direction of SH mean, yes, it's going to tell us the direction of fracturing, right? So, for example, if we had SH mean going there in the direction of the horizontal wellbore, and for these stress conditions, that will tell us that the fracture is going to be perpendicular to that. But what else? What else is that going to give us, SH mean? What about the value of SH mean? Any clue?
The pressure of our fracture is like
The pressure, the absolute minimum pressure needed in order to open a hydraulic fracture, or what is called an open mode fracture. So now that we know that if the pore pressure in the rock goes at this depth above that limit, very likely you are in a region which you are very close to open a hydraulic fracture. We're going to see later on it's not exactly that value, but actually you need a little bit more of pressure to overcome some viscous forces, to deform the rock, to make fluids go into the fracture. But if you want to design the pumps that are going to be in the surface here, that are needed to pump all these fluids inside the formation, you know that at least the pressure that you need is going to have to overcome that minimum principal stress. So in other words, how is that called? Starts with F. Any guess? Well, while you think, let me write some equations that you already know, okay? And let me just assume in this case, this is SH max. And we know that, and let's simplify it and call it SH. And we'll do here the simple case, but it's the same is valid for the other case. If I don't have tectonic strains, do you remember what is the value of the effective horizontal stress? So we already know this, right? Total stress equal to effective stress times pore pressure. But what is going to be the horizontal stress in the absence of tectonic strains? This is an equation that I'm not going to ask you to know by heart, but you should try to remember. And very well. Times what? Vertical stress. right? Okay, very good. So, and what is the effective vertical stress? Something very important here is that usually effective stresses are very important, but we cannot really either measure them in the field or, well, that's the issue. We cannot really measure them or calculate them. And instead of that, usually either you measure horizontal stresses or you calculate total vertical stress. But effective stresses are very difficult to measure or to calculate directly. So instead of that, what sigma v is going to be the total vertical stress minus the pore pressure, right? So I didn't do anything new so far. And from here, you see that now I can write this equation as this guy is going to be times SV. And now I have pore pressure here, I have pore pressure there, and this is going to be common denominator, this one, and this is going to be, let me see. One minus what? You know, it's very difficult to do math in front of people. If I were to do this on my own, that it would be very easy. But what? Okay. Remember, this is a Greek letter nu. Okay, it's not a b. So it will be. Let's see. It will be 1 minus nu, and this is going to be 1 minus 2 nu, right? You agree? Okay. Let me check if that's okay. Yeah, that's okay. Times pore pressure. And this is the same equation, but now expressed in terms of vertical stress and pore pressure. So you can calculate what is the horizontal stress, the total horizontal stress with the total vertical stress and with the pore pressure. But now let me do just something very simple but very meaningful. I'm going to divide this SH by an amount delta Z. And actually what I'm going to do is I'm going to take the derivative of this. So the derivative, if I use deltas instead of these, the derivative of SH with respect to Z is going to be, this one we're going to assume is constant. Does vertical stress change with depth? Total vertical stress? Yes or no? Yes, right? So we cannot ignore it, and it's going to be that. And what about pore pressure? Does pore pressure change with depth? Yes, so we cannot ignore it either. What is this? We already know this guy. Vertical stress gradient, right? Total vertical stress gradient or if I want to write it more compact, will be the lithostatic gradient. It's the same thing. What about this guy? Wait. I'm missing here 1 minus, right? What about this guy? We already know that one too. Remember that hydrostatic is just an assumption to make things easier. It doesn't work all the time. Actually, most time it doesn't work. So in general, this is going to be the pore pressure gradient. And we get to where I wanted to get, which is, what is this? I know you know it. It starts with F, and it's a gradient too. What? No. The fracture gradient, right? So you remember that before we were talking about fractures. So what is the pressure that you need in order to open a fracture here? It depends on the minimum principal stress, and it depends on a few more things. But now we're going to simplify it, and the lower bound for that fracture gradient is going to be this. This is the fracture gradient. So now, by knowing what is the horizontal stress, we can calculate what is the fracture gradient, which is with this number, you will calculate what is the amount of, or what is the value of the density in the drilling mud that you will need to open a fracture if you were drilling, or with this value also, this one times depth will give you the pressure needed in order to fracture a formation at that particular depth. So horizontal stresses are very, very important in geomechanics. And now with elasticity, we have found a way to calculate those. In the homework, the last problem, if you haven't started with the homework yet, let me anticipate that in the last problem here, you have exactly that. You know the depth, the Barnett shale, you know what is the gradient of total vertical stress, you know what is the pore pressure, and here in this case hydrostatic pore pressure gradient for the first part, and if you know what is the Young modulus, what is the Poisson ratio, you can calculate those stresses, and knowing those stresses, you can tell what is the minimum pressure needed in order to fracture that formation. So if you go over here, you will see here it gets a little bit more complicated, and you have additional tectonic strains. And when you have those tectonic strains, you have to consider also the Young modulus. And also you have an overpressure in this case. In the Barnett shale, there is no hydrostatic pore pressure. The pressure is actually higher than that. Okay. Any question? This is the same thing that we have seen so far. It's just I wanted to give it another twist and calculate this fracture gradient based on these equations. But it's exactly the same thing that we have seen before. Yes,
Mr.
Mr. Awa.
For derivations on the exam?
No, I'm not going to ask for derivations. The only thing I'm going to ask is working out these problems of elasticity with the matrix and knowing what are the strains or what are the stresses to calculate a given modulus. By the way, I'm going to give you also practice exams, okay? So if I don't do that by Friday, please send me an email, remind me that, so you have time to practice with those. Okay, so we have seen the concept of fracture gradient. I'd like to talk now about another application of elasticity, which is very important. Do you guys remember the pore pressure diffusion equation, or in the diffusivity equation in general? Anyone remembers that by heart? I should, but I don't remember it quite well. But it's something like this. It tells you the variation of pressure with time. It depends on, and this is where it starts to blank, okay? It's, I think, K divided viscosity and compressibility, something like that, okay? And that tells you the variation of pressure in space. This is in 1D. But something very important here is that when you solve any problems related to fluid flow as a function of time, as a function of space, like if you're draining the reservoir or injecting a fluid, then you need to solve this equation. And this is actually what you do in reservoir engineering. You just solve this equation. It's a little bit more complicated than that, right? But you're just solving that equation. A critical parameter in this equation is, in addition to permeability and viscosity of the fluid, is the total compressibility of the formation. And that total compressibility is composed by the compressibility of the phases. For example, if you had gas, it will be the compressibility of the gas times, let me change this to right before the volume fraction coefficient. It will be saturation of gas times compressibility of gas plus saturation of oil times compressibility of oil plus the saturation of water times the compressibility of water. If you had some other fluid, let's say like nitrogen of CO2, you will put it in here, okay? Plus one more coefficient, which is the formation compressibility or the rock compressibility. When you change the pressure in a reservoir, the volume of the pore is going to change, right? Let's do an example over here. So let's say that you're producing from a formation at a given depth, and you are changing the pressure with time. And here you have a piece of rock which originally has this volume given by that square. And let's say that on top of this you have a shale which is applying an overburden stress to that reservoir. And as a function of time, what we're going to do, we're going to pump, right? So if we pump fluids out of here, you could inject too, okay? It's a similar problem, but let's work with the problem of pumping. What is going to happen to the pore pressure with time? It's going to decrease, right? So the pore pressure, the bottom hole pressure here, you want to decrease that in order to be able to pump. What about the vertical stress? I don't remember if we went already through this problem or not, but what happens to the vertical stress, the total vertical stress? What do you think is going to happen to it? It's going to stay the same, it's going to change. By depleting these fluids, are we going to change something over here? Is the weight of all the rock on top going to be the same if we do a change over here? The answer is yes. Okay, you're doing changing fluid saturation here. You're changing porosity here. But if you have a very good cap rock, you're not changing anything above it. You're not changing the weight of the rocks above this. There's a lot of stuff above that. You are not changing that weight. And if your cap rock deforms as you produce, also the vertical stress is not going to change. If you have a very steep cap rock, that may be different. Okay, some of the cap rock may support some of the weight on top. But let's assume this is a cap rock made of a ductile mud rock, so all the weight goes on the reservoir. Because of that, the vertical stress is not going to change. It's going to be constant with time. And the only thing we're going to do is we're going to increase the effective stress in the reservoir, right? Every time that you lower more and more the pore pressure, you increase more and more the effective vertical stress. And what do you think is going to happen to the effective horizontal stress? It's going to increase too? It will. If if we assume these conditions in which there is just strain in one direction, and this element of rock now, it becomes smaller, and just in one direction, the horizontal stress is going to increase too. But let's not get there yet. Later on, we're going to see equations that are going to tell us what is that variation of horizontal stress. But what I want to do now is to calculate this value, formation compressibility. Okay? By definition, this value formation compressibility, that in order to be a little bit more rigorous, we're going to call it CPP, is the pore volume compressibility, is defined as the change in pore volume due to a change in pore pressure divided the original pore volume. Considering that vertical stress is going to be constant and there is not going to be any horizontal stress, that's going to be constant too. If you remember, guys, when you do these sort of partial derivatives, then you add a line here, and those things that are here, that means that those remain constant. So SV remains constant, epsilon H remains constant. There is no variation in that side. This one is called the pore compressibility. And this one is very important because we know that when we lower the pressure, the rock is going to get smaller. And if the rock gets smaller, the pore volume is going to get smaller too. And do you think that's good for production or not? Why not, Mr. Su? It's actually reducing the pore space, right? Reducing the pore throats and lowering the permeability. And that's not good. That's not good, certainly. But it has the advantage that when you're also reducing the pore size, you are squeezing the rock and facilitating the fluids to move in the rock. So it's like squeezing a sponge, right? If you can squeeze the rock, you're going to get more fluids out of it, and that's going to be the compaction drive. So it's good and it's bad, okay? So it depends on your rock, and it depends how bad your permeability can get. Actually, I had one student there, I think he presented yesterday, a paper about this problem and doing numerical simulations of that, of how permeability decreases, but then you have more compaction drive, so trying to study that. So he was presenting at ATC in Dallas. Okay, but let's come back to this. So this is going to be the pore volume compressibility. There is another type of compressibility which is called the bulk compressibility.